I start with the discussion of Computer Go. Computer Go changed game programming scene in the latest developments. For a long time, it wasn't solvable at a high level, but in the last decade, there were two important developments. Monte Carlo tree search and machine learning with deep convolutional networks. On their own, none of them was enough to beat high quality human players, but together they did. In the last 2 years, there was a very fast development of computer strength in Go. But what computers? The computers were huge, or the time was huge. For example, the AlphaGo latest version used 5,000 first-generation TPUs. That is equivalent to about 20,000 high-end GPU cards for the learning and data preparation phases. They trained AlphaGo only for 39 hours, and the newspapers were full of this short time. But actually, it means 80 GPU years, the full training. And the other problem was that no code or data, the weights, was available for the public. Only public publication and game results were available. That is why an internet community group led by Giancarlo Pascutto started a project. Lila was a standalone Go player, and they developed it into a machine learning version of AlphaGo, that machine learning reimplementation of AlphaGo. It is still running about 8 months now. On the average, we have about 200 computers always at work in some place of the world. But it is still far from the level of AlphaGo strength. But it still continues to improve. Today, up to date, they played 8 million games, and from there they constantly modify the weights. Another re-implementation was the Facebook research project. They also developed Go programs, but they couldn't achieve AlphaGo level in time. So after AlphaGo was published, they also re-implemented it with their own, again, huge hardware with 2,000 GPUs for 2 weeks. The training was, it's again about 80 GPU years if we reduce it to one machine. How they work? Very simply stated, they start from random ways, play a set of games, and they play the game to the end, and they score the finished game according to the rules of Go. And then they go back and they assign the outcome of the whole game to each individual position. That, for example, if black wins, then all the black moves are considered good moves, and all the white moves are considered bad moves, losing moves. Then they have a large amount of positions, and they put it into a large set, and they randomly sample it and train a new model with these scored positions. After some training, they play a match between the new model and the old model, and if the new model is better, then they replace it with the old one with the new one. What is the cause of the huge computational need? Not the machine learning itself, but the self-playing games. That is the first first move, that is providing high-quality games for the machine learning. That is what it takes the huge amount of time. They are used mainly in the Monte Carlo tree search for policy and value estimation. I was thinking on how could we reduce this large computational needs. This is the real problem. Each network update costs about 1,000, 2,000, or 3,000 network evaluations. So very, very high amount of evaluation for updates. So that's what I wanted to reduce. So I think that, I thought that value iteration may be a better approach in the long run. Value iteration is that we have a position, each position, we assign to each position a value, and we have the state function, how to change from one position to the next position. It depends on the rules of the Go, and and we compute a new value of the position by taking all the successor moves and finding the best of them, maximum or minimum, depending on whether it is black or white. Of course, we cannot store this whole value data because there's an immensely large number of positions. So we use machine learning, that we use only a restricted set of parameters and modify them. So in parallelization of this approach, it is easily parallelized on itself because they simply independently computes all successor positions and takes the maximum. We don't use Monte Carlo tree search, and no policy network is then only the pure value iteration is used. So this is the simplest form of algorithm. Find all successor move and take the minimum or maximum. Another simplification for speed up is that during the training, we don't need to find the absolutely best move. We are interested only who wins the position, and then that's why we simply round the maximums, and so we don't have to compute all of them, because if we find one move that is good enough, then we don't have to look at other moves which are even better, but because we don't want to play this move, we just want to qualify our positions. So that's what we do. This is actually the alpha cutoff in research. However, there is an inefficiency problem in the parallelization, because we have to give as large chunks to work for parallel execution as we can, because otherwise the parallel resources are not used good enough. On the other hand, if we use this kind of early exits for our alpha cutoffs, then many painfully obtained results are discarded because they are not needed. The problem is that the early exits happen irregularly. Some positions we can decide easily. Other position we have to take a lot of successor moves. One solution for this is to assign a new work to the unused time slots. That is, similarly to Tetris, we only give the parallel execution always a full set of work, and in the meantime we work on the assignment of new work to the free time slots. Fortunately, not fortunately, but the network evaluation takes quite a long time in the millisecond range, so there is plenty of time to make these assignments. They are not critical. In all, they result in a speed up of about 2. Here is, for example, a training log excerpt. Here we have a position where it is a hex game position. We have 36 pieces, and there are 48 next moves, 48 next legal moves in this position. And we have 200,000 positions. So in total, 90 million positions should be calculated. But using this alpha cutoff early exits, we can solve the same problem with only 49 million evaluation, and it means about a speed up of 2, and it is needed because this process just to qualify the 200,000 positions takes about 3 hours on this machine. And then comes the actual training, which is only 2 hours. So the data preparation is much longer than the actual training. All this approach works from the outcomes of the game, because that is the only thing which we know about the game without analyzing it in detail. If we see, for example, this position, what is the value of this position? It depends on what game it is. If it is Gomoku, it is 5 in a row, then it is a 1 position for black. If it is Go, then who knows what is the outcome. It is an unfinished or undecided state in Go. We use the hex for our experiment. Hex is placed on a hexagonal grid. It is known that no strategy exists to beat the first player and no draw exists, so that means that the first player has a winning strategy, but no one knows it, how to make this strategy. There were in the recent, in the last decade, mostly in the last decade, a lot of work in solving opening positions in hex, and these are actually as I know currently the all solved opening positions in chess. It means, for example, that here if the first mover plays the black stones, then it wins. If the first mover plays the white places, then it loses. But for example, this is a 9x9 board. This is the only one. The larger boards are not solved. The only one that is solved fully. But even in some cases, for example, if I remember this one or this, some of these stones took 100 days to run in a sufficiently good machine. This hex can also be played on a Go board if we add diagonal connections in one diagonal. The other diagonal is not included. And this because it's very useful for us, because convolutional neural networks are developed for this kind of structures, rectangular arrays, basically. So our experiment is the following: a 9x9 board. That means 81 squares. So the piece level, that is how many pieces are on the board. There are 82 levels from 0 to the fully populated board. We use the value network, a deep convolutional neural network with 12 residual blocks. And at each level, 32 filters. I don't want to go into details of of what a filter is or residual box. Input is a row position. Each point is either black or white or empty. There is no preprocessing of any kind connected to hex. And we score the positions by simply according to rules. If it is won by back, that is, it is finished and connected, or if it is won by white, or in any other case, it is unfinished. Unfinished means that it is the network that has to solve it for himself, the estimation, and learn it. Input volume was 200,000 random position for each piece level. That is 82 times 200,000 random positions was. So random positions meant that we didn't have to provide high quality games, only random position which could be easily generated, even with this simple scoring which is very fast. And it was trained for 6 epochs at each piece level. That is the 82 times 6 epochs. That was the whole training, and it was programmed in Keras and Python, and the training was about 2 weeks on a simple machine. No GPU was used, only multi-core. Result. It was a good outcome for, at least for us, reasonably, but it is still far from the good specialized hex player. But there is nothing, no domain knowledge built in it. It doesn't even know the program, it is finished. If it is reached the final position, it plays through the end. Its strength still has to be qualified. In the following, I will show you a simple position and how it plays. But before that, I will the final summary. Value iteration is promising. I don't know if it achieves the same amount of strength, the same level of strength as the other programs, but I was quite satisfied with it. And with GPU support, maybe a single machine is feasible to achieve high level of play. Now let's see the game. Egy pillanat, ez gyors lesz már. This is a random position of 30 pieces. It is red to move. Red is in a dangerous position because here are the blue stones, and if blue connects here, then there is no way that red could cut him from connecting. And here there is a so-called bridge, which is actually a virtual connection, because also there is no way that red can cut white here. So this is an absolutely important move. That's what the program played. The next thing is, now it is blue's problem, because red has a almost perfect path going from top down. So eventually blue has to play here. Blue, however, first introduced another move, which was a forcing move. Doesn't change really the position, but it is not a bad move. Of course, red defender saved the bridge, as they say. Now, blue played the correct move, and now again blue has the upper hand, because if he connects here, then the game is finished. So red has to play there, as he did. This, however, threat, if red plays here, then it connects, and blue has to do something. And now comes, which is a brilliant move. this plate. Also, this plate could have solved the connection, could have prevented red from connecting. But this is better. This move would have been a losing move if he played here. Why? Because a moment. No. If now blue has a connection thread here, so in order to stop it, red has to play one of these three positions. Otherwise, blue wins. However, if red plays here, then blue could play here, and there is a way to win this situation. If blue had played here, then red would have played here. That means that it would have had a threat again to connect. So blue should have to defend here, and then red would have time to stop this attack, and red would have won. But this move avoids this problem because there is no forcing move here for red. Sorry. Red tries some simple forcing move, but there is no way for him to get away. He resolved this problem, but now blue pushes through. Blue plays the only move that defends against this attack, but there are some forcing moves of blue, and there is no way that he can stop blue from connecting. And blue won the game. So it is interesting that a program without any searching and any analyzing of the game could achieve only through machine learning this level of play. Thank you for your attention.
Thank you very much.
So in these games we have also always wait until the end of the games to evaluate the results. Isn't there a means to assess the value of a position to fasten the evaluation?
That's the problem. What the AlphaGo and others did with the huge hardware is that they qualified all one-side moves, all moves of one side to win, or the others would lose. But it's not a very good thing, because if you ask two grandmasters to play a game, they play a good game, one of them wins, that it doesn't mean that the other played bad moves. Most large part of his moves are completely correct, but we learn them as bad positions. So it really destroys the effectivity of learning, because we teach false data. And that's why they need 3 billion positions to evaluate, and each position needed 1,000 evaluation, and that was what I didn't like, and that's why I tried to go in this direction. Thank you.
Okay. One more.
Thank you very much for your presentation. I enjoyed it really much. Yes, when I said that this is an open source community, DeepMind's results are not so much open because
yes.
The facts you said. I have two questions. The first one is that how did you choose your architecture with the 16 residual blocks? Okay, and it is working.
That's simply It is a question of available time. For example, now I'm training a larger network, which is 16 residual blocks deep and 64 filters.
I see.
But it will take about 3 or 5 weeks. So the next step will be to use GPUs, because up to date I used only simple machines.
Yes, I see. And thank you. And my other question is, I was always thinking of this AlphaGo Zero, that they are teaching it on this huge amount of computation power. And people say that the complexity of Go is about the possible situations on the table is 10 to the power of 170, and the complexity of chess is 10 to the power of 120.
Yeah.
And
40 or I think.
Or 40. So it's of course a huge difference, but we know that the chess is analytically solved by the IBM Deep Blue in the 1990s.
It was not solved. It is also a approximation.
Yes,
it was solved enough to beat Kasparov.
Yes, I mean that it can operate on superhuman level,
yes.
In an analytical way of solution. And what do you think?
It was not analytical. They evaluated a huge number, 200 million moves in each, 200 million possibility in each position.
Yes, but it is not a machine learning.
No, there's no learning.
I mean by analytical.
Searching.
Yes, by a big search. And what do you think if with such a computational power that the Google has would be applied in this kind of search to Go? Wouldn't be it similar to the convolutional net solution? So I mean, if we just would make searches from all the situations with such a big computational power. So if we compare the complexity of chess,
they do search. They do search with the Monte Carlo tree search. They actually in each position, whatever we do in machine learning. There will be always a better program with search, because it is in the actual position where it works, and machine learning is in the whole. Unless we solve it perfectly, the game, then there's no need for search.
Okay. Thank you very much.
Thank you.